have three existing gas laws that we've discussed so far. We have Boyle's law, and Boyle's law is going to be the one that is P1V1 equals P2V2. The next one that we're going to talk about is going to be Charles's law. Charles's law says V1 over T1 equals V2 over T2. And we have Gay-Lussac's law, which is P1 over T1 equals P2 over T2. So, in Boyle's law, the pressure and the volume change, but the temperature does not. And so what we have going on here is, in this case, is the temperature is going to be a constant. In Charles' law, the volume and the temperature change, but the pressure is a constant. And in Gay-Lussac's law, the pressure and the temperature change, but the volume is a constant. And so we have something that works as long as only two things change, but one of them has to stay the same. The question is, what happens though if all three of the things change? We change the pressure and the volume and the temperature, and they all change. If that happens, you can't use Boyle's law or Charles' law and Gay-Lussac's law, but instead we could sort of take all three of these and we can merge them together into a combined gas law, because it combines these three laws. And the combined gas law is what we have down here at the bottom. P1V1 over T1 equals P2V2 over T2. And so the original pressure, P1, and we have then that times the original volume, V1, times the original, divided by the original temperature, T1, equals the final pressure, T2, times the final volume, V2, divided by the final temperature, T2. Now, in this case, the same rules as far as units apply. Pressure can be pretty much in any unit that you'd like, as long as it's a unit of pressure, and as long as P2 has the same units as P1. Volume, the same thing is true, is that we can have whatever units of volume that we like, as long as it's a unit of volume, as long as it's the same as the unit of V2, and temperature works the same way as before, in that it always has to be in Kelvin. No choices there. So it is the same on both sides, just sort of automatically. So let's take a look at how we might go about doing one of these problems. And so to do that, we're going to sort of move a little forward here. And so here's our example, is that what we know is a 15.6 liter container of gas is collected at 801 torr and 24 degrees Celsius. What is the volume of the gas if it is brought to STP? And so basically what we're going to do in this case is we first want to write out our combined gas law. Combined gas law says this: P1 times V1 over T1 is going to be equal to P2 times 2 times T2 times V2. Let me correct that right there. Get rid of that there. P2 times V2 over T2. And so to do this, let's see what we have for our original pressure. So our original pressure, 15.6 liter container of a gas is collected at 801 torr. And so original pressure is going to be 801 torr. And so this simply means that the final pressure has to be in torr, times the original volume, V1, and it says that's 15.6, and so 15.6 liters, all over the original temperature. And the temperature that's mentioned here is 24 degrees C, and so to work this out, we're going to have to convert this to Kelvin. So 24 degrees C plus 273.15, and so if you go ahead and take out the calculators there if you need them. So we get 297.15 Kelvin is what we get for this. And so on bottom, 297.15 Kelvin goes down there. And this is going to equal to P2, the second pressure. Well, it says that it's at STP, and if it's at STP, then standard temperature and pressure, and so standard pressure in torr is going to be 760. And so we get 760 torr on this side, times the volume, the volume afterwards, and we don't know that. That's what we're looking for. And so this would be just V2 right here. The unit's going to have to be in liters because that's what it was on the left side. It's the unit we started with, divided by the temperature. Now it's STP, standard temperature. Standard temperature is 0 degrees Celsius or 273.15 Kelvin. So this is what we have here. So we want to solve for V2. And so to solve for V2, we're basically going to do a little bit of cross multiplication. So we can do 801 torr times 15.6 liters divided by 297.15 K. But we want to take the 760 and move it on bottom, the 273.15 and move it on top and multiply those up. And that should give it to give our final answer here. And so if you once again take out the calculators here, 801 torr times 15.6 liters, and then times the 273.15, because that's being cross-multiplied up to the top, and then divided by 297.15 K, and we also divide that by 760 torr. And so when we do that, we end up with an overall V2 of 15.113 liters. Significant figure-wise is that taking a look at that, what we see here is that our original 15.6 has 3 significant figures, 24 degrees has 2 significant figures, 801 torr has 3 significant figures. And so normally we'd have 2 here, except for the fact that this one right here is round to the ones place for your temperature. And so when that comes over here, that'll be around the ones place here, which gives 3 significant figures. And so and the 273.15 is exact. So that means that we're going to have 3 significant figures for our final answer. So 1, 2, 3. And so our final volume here is going to be 15.1 liters. And so that will be our final answer here. That's how you go about using the combined gas law. Pretty much you just take what you've got, you put it into the combined gas law equation, make sure your units match up, and cross-multiply to solve. And so that's sort of how that works. So let's carry on here. And so continuing, we've got another example here. So in this case, what we know is a weather balloon is measured to have a volume of 310 liters before lifting off when the ground conditions are 102 kilopascals and 18 degrees Celsius. The balloon then rises to an altitude where the pressure is halved, and it's found at that point to have a volume of 480 liters. So what's the temperature at that altitude? So let's go ahead and set up our ideal gas, our combined gas law. So we know P1 V1 over T1 is equal to P2 V2 over T2. And so what's the original pressure of the weather balloon? Let's see, pressure of the weather balloon, it says 102 kilopascals. And so we'd say 102 kPa times the original volume of the balloon. It has a volume of 310 liters. So times 310 liters divided by the original temperature, which is 18 degrees Celsius. And so once again, 273.15 plus 18 degrees Celsius. And so doing this gives us 291.15. I'm doing the math right, Kelvin. So 291.15 kelvins. And so we've got that equals P2. And it says the balloon rises to the altitude where the pressure has halved. And so originally we had a pressure of, as we said, where was it going here? Of 102 kilopascals. Half of that would be 51. And so I know I have a pressure of 51 kPa. It says that it has a volume at this point of 480 liters. So 480 liters like this, divided by my T2, which I do not know because it asks what is the temperature at that altitude. So once again, we're going to go ahead and we're going to cross multiply this guy. In this case, what we're going to have to do is we have to get this T all by itself. So we're going to have to get the T2 up top. And so in doing that, we're going to have to move the 291 up here, and we're going to have to move these two guys down to the bottom. So that effectively what we're going to have is that to work this out, we've got on our right side our 51 kilopascals times our 480 liters. And then you're going to multiply that times the 291.15 from the bottom of the left. And then you're going to divide that by the two guys on the top on the left, which are 310, and then divide that by 102. So overall, is that what we end up getting for this is that T2 is equal to, unrounded, 225.40 Kelvin. Significant figure-wise is that we have 3 significant figures for our kilopascals, originally, we have two significant figures for our one that's after it's halved over here, two significant figures on our volume in liters, two significant figures on our volume in liters over here. So we're going to have two significant figures here. And so T2 would be 230, that's a 3, kelvins. And that would be our final answer here using the combined gas law.